You know, we interact with software code pretty much every minute of every day. But what about the actual hardware that code runs on? How do you write code for a physical microchip? Well, today we're going to pull back the curtain on Verilog, the language that's basically the architectural blueprint for our entire digital world.
So here's our game plan. We'll start with what makes designing hardware just so different from software. Then, we'll dive into the biggest mental shift of all, thinking in parallel. After that, we'll break down the two main jobs of any circuit, peek at some basic Verilog code, cover the super strict rules you have to follow, and then see how it all comes together to build the tech we can't live without.
All right, so let's get right to it. Let's start with the big question that even leads us to a language like Verilog. We all kind of get how an app works, right? It's a series of instructions that the computer follows one step after another. But a processor, that isn't a list of commands. It's a real, physical thing with millions or even billions of tiny little components all wired together. So how in the world do you describe that? Well, the answer is something called a hardware description language, or HDL for short. And this is the most important part. An HDL doesn't run like a normal program, it describes a physical object. It's not a list of things for a processor to do, it's the instruction manual for building the processor itself. The absolute best way to think about this is the recipe versus the blueprint. Software code is like a recipe. You do step 1, then you do step 2, then step 3. Order is everything. Verilog, on the other hand, is the full architectural blueprint for a house. It shows every wall, every wire, every outlet, and all those things exist at the same time in the final building.
And that idea of a blueprint brings us to the most crucial and, honestly, the hardest concept to wrap your head around when you get into hardware design.
In software, if you write C equals A plus B, it's an action. The computer has to know A and B before it can calculate C. But in Verilog, that line of code isn't an action at all. It's a description of a physical circuit called an adder. The wires for A and B are the inputs, and the wire for C is the output, and they all exist at the exact same time. You're not telling a computer what to do in order, you're just describing how a thing is built.
This is really the mantra you have to just keep repeating to yourself. It's not a sequence. It's a huge collection of components, all working in parallel all the time, constantly reacting to the signals they're getting.
So if everything is happening at once, how is it not just total chaos? Well, think of a chip as a giant orchestra. You've got the strings, the brass, the percussion. They're all playing their own parts simultaneously. What keeps them together? The conductor. In hardware, our conductor is the clock signal. It's a super fast, steady beat that tells every single component when to make its next move, keeping everything perfectly synchronized.
Okay, so if we're thinking of our chip as an orchestra, let's talk about the two main types of instruments we can actually describe in our blueprint.
First, you've got combinational logic. You can think of this as the brains of the operation. It takes in some information and instantly calculates an answer, kind of like a simple calculator. If the inputs change, the output changes right away. Then you have sequential logic. This is the memory. It holds on to a piece of information, we call that its state, and it only changes or updates that information when it hears the conductor's beat, that tick of the clock. The little circuit that does this is called a flip-flop, and it's the basis for all digital memory.
So how do we actually write the blueprint for these brains and memory components? Let's take a quick look at the core Verilog syntax that lets us describe them.
Verilog gives us a few key tools. There's something called an always at curly brackets block. That's how you describe the brains. It basically says, hey, always recalculate this result whenever any of the inputs change. Then there's the always at pose edge clock block. That's how you describe the memory. It says only update this value on the pose edge, the rising edge, or tick of the clock. The assign keyword is for wiring things up simply, and then you package all of this stuff into modules, which are like reusable digital Lego bricks.
Now, you might be thinking that since you're just describing things, you can be a bit loose with the rules. It's the complete opposite. Because you're making a physical blueprint, the rules are unbelievably strict.
I mean, think about it. If you have a bug in your software, you can push an update. If your Verilog blueprint is fuzzy or ambiguous, you could spend millions of dollars making a chip that is fundamentally broken. The bug is literally etched into silicon. Your code has to describe something that can actually be built, with zero confusion. And that brings us to what is probably the #1 point of confusion for anyone starting out. There are two ways to assign a value in Verilog, with a single equals sign or with this little less than equals arrow thing. They look almost the same,
but they describe two totally different physical things.
Luckily, the rule is really simple, and it connects right back to our two types of logic. For combinational logic, the brains, you always use the regular equal sign. This describes a direct, immediate connection, like a wire. For sequential logic, the memory, you always use the little arrow. This perfectly describes what a memory element does. It samples a value on the clock edge. Just following this one simple rule will prevent an entire class of really nasty bugs.
And there are a few other golden rules. Never mix these two types of assignments in the same block. Never try to have two different blocks drive the same wire. That's a physical short circuit. In your brain's logic, every if statement has to have an else. If you don't, the blueprint is incomplete, and the tools might create a weird unintended memory element called a latch, which causes all sorts of problems. And finally, always give your memory a reset signal so the chip boots up in a clean, predictable state.
Okay, so we've looked at the big ideas, the code, and the rules. Let's zoom back out now and see how this all comes together to literally build the world we live in.
It's really all about using these basic ideas, describing logic and memory, and then connecting them together in these modular Lego bricks. Engineers can start with a blueprint for a simple adder, connect those to make a calculator, and just keep connecting those modules together until they've described an entire complex microprocessor.
And the scale we're talking about here is just mind-bending. Some of the most advanced chips being designed today have over 250 billion transistors. And every single one of those tiny microscopic switches is placed and connected based on a blueprint that was written in a language like Verilog.
So that kind of leaves us with a final thought to chew on. We are now designing digital systems that have a complexity rivaling a major city. As that complexity just keeps exploding, how will the very languages we use as our blueprints need to change and evolve just to keep up? That's one of the biggest challenges facing the next generation of hardware designers.